will help me improve the talk in the future if I know like which pieces are difficult to understand. My name is Lauren. I'm a developer relations engineer at them.I'll, and previously I worked on our Node runtime and wrote a book on GraphQL and was a longtime consultant and open source maintainer. Today we'll look at durable execution, and I'll define what that is and describe it, and then I'll talk about some new possibilities that it opens up, and I'll go briefly into how it works, and then go through some system design patterns. I won't assume you know any of them, so I'll try to give a concise explanation of what each is, and then I'll talk about how you either don't need it in temporal or it's made much easier. So, what is durable execution? It sounds kind of weird. First, let's talk about normal execution. So there's an important property of normal execution, which is that functions fail to complete executing in many situations, including when a process crashes, maybe you divide by 0 or have an uncaught exception. Maybe the process was killed by the OS because you're running out of memory. Maybe the machine loses power. Maybe you're deploying new code, and usually you have some graceful shutdown period so that the existing code can finish handling requests before it stops, but maybe you have something that takes a long time. Maybe you have a long sleep or some retry that's not done retrying, and you get cut off by the hard sig kill at the end of the graceful shutdown period. Transient failures, so a common thing is to have some dependency that you're calling. Maybe it's a database that you can't reach, or a downstream service that's unavailable, or returning error codes at the moment, or a third-party service that you're unable to reach. And you have to either let those errors throw or retry, catch and retry. So durable execution provides functions that are guaranteed to complete running. So let's say we have this process order function, and it has 3 steps. First, we talk to the inventory service and we reserve the inventory, the product that's being ordered. The second step is we charge the user for the order, and then we send a package with the fulfillment service. And if we successfully do the first 2 steps, lines 2 and 3, and then the process dies, interrupted, for any of the reasons we talked about before, we won't have sent the package. And we don't really know that we haven't sent the package. We have to sort of like look at the charges database from the charges service, and then look at the fulfillment service and see what it's done, and notice that there's a discrepancy there. But the default, unless we're like figure it out, we've charged the user and we haven't sent them their order. So in durable execution, we guarantee that this will complete running. And the way we do that is, once a process in production crashes after line 3, the library in the system the durable execution system will continue running this function on another process in the same state. So the next line that will be run will be line 4, and all state will be intact. So local variables, call stack, threads will all be the same. So that's the basic how durable execution works. Is whenever something goes wrong with your process, it'll be automatically run on another process or machine. In addition to that, transient failures are automatically retried. So any of these 3 service calls, if there are transient errors, then the system will automatically retry, and I won't have to take care of catching and doing the retry logic myself. By default, it's retry forever, so no maximum attempts and exponential back off, but you can configure that if you like. And then I guess failures that are non-retriable, that aren't transient. So like if I tried to send a package and the order.address was some non-existent address, and UPS returned to me some failure like this address doesn't exist, then the non-triable failure would throw and not get retried. So durable execution is coding at a higher level of abstraction, sort of like if we're in Java, we don't have to memory manage like we do for in C. When we are writing durable code, we're it's a level of abstraction that is higher than concerns about whether there's faults in the infrastructure I'm running on. That's both the processor machines that are running me, and it's also transient failures in any dependencies, like database service, API. So we've got this new programming primitive, this durable function thing, and it's pretty different from the normal functions, which are volatile in that they can die at any time. And it turns out that a lot of the way we code, a lot of our design patterns are predicated on the assumption that our functions might die. So we're constantly like checkpointing state, or doing like a state machine and workers and in queues, so that we're only doing a certain part of a process at a time, and anything that we didn't save in the database we don't consider to have been done reliably. So that's sort of like a core tenet of distributed systems or system design when you're trying to do things correctly and maintain consistent state and default tolerant. And a lot of that we don't need to do if we have this durable function as a primitive. It also opens up some new possibilities of how you program. One of those is that you can sleep for an arbitrary period of time. So normally, this is a JavaScript, but normally I can't sleep in production Java code for this long period because A, I don't have faith that my process will be around in 30 days. I probably will have redeployed by then, or yeah. And secondly, I don't want to take up a thread sleeping this long. I'm going to run out of threads. So the two ways that durable execution solves this is that one, this under the hood, this call is translated into a gRPC call to a server or a cluster that has a database, and there's a 30-day durable timer that's set in the database. When that goes off, this code will continue running. So so the system reliably continues running this function at the end of the 30 days, and also it doesn't take up resources besides that entering the database. It's not taking up a thread. It's smart enough to know that like this function hasn't been doing anything for a while. I'll let it go out of cache and make room for other functions, or in the case of Java, methods. When you have these long-running methods, it's gonna like hurt my brain a little bit to try to replace every time I set function with method.
Don't worry about it. Just keep talking.
So once we have these long-running functions, we want to be able to send RPCs to them. We want to figure out what their current state is. It's been like 5 days. What's going on? Function. And we also might want to be able to give them further instructions. So we can send RPCs to durable functions. We can also have them run forever. So something called the entity pattern is or digital twin is you have a long-running function that represents some business entity or business domain model. And one example would be like a customer loyalty program. If a user signs up for your product or your company, and you can start a loyalty program function when they sign up, and then that function can take care of all the logic associated with their membership in this program. They can make decisions on when you get new points, what happens like when you get to a new level, notifying you that you got to a new level, and yeah. You can be sending RPCs and to figure out the state of this customer's loyalty membership thing. You also, it turns out, don't need to use a database. So if you have this function that can't fail, you can just put state that you want to save in local variables, and trust that it will always be there. Because you can keep that function running, and you can send RPCs to check out what the current state of those variables are. I'll go through a couple of code examples. This is JS, a subscription function that you call with a user object and an amount to charge them every month. We start out with canceled false. We set an RPC handler for the cancel RPC. Whenever that's called, it'll set cancel to true and send an email to the user saying your subscription has been canceled. And the main body of the function is, while we're not canceled, or until we get canceled, charge the user and then sleep 30 days. And once we get to that sleep 30 days line, this function can go out of cache and only be woken up either when the 30-day timer goes off or when the function gets a cancel RPC, in which case it'll be woken up to call the cancel handler. Another thing to note is that the send an email and charge, if they're both talking to service like Mailgun and Stripe, if Mailgun or Stripe are unreachable currently at the moment, they'll automatically be retried. Here's an example of the loyalty program forever function that you call at the beginning when the user signs up. You start out with points at 0. You set 2 RPC handlers. The first one is notify purchase. That takes in a purchase object and based on the total amount in the purchase, adds some number of points to your points total, and then if you pass a certain threshold, does something like sends you a coupon. And this notify purchase RPC can be called from anywhere else in your backend whenever the user makes a purchase. And then the other handler is get points. So if the user logs into their web portal for the company and looks up their profile and their number of points, instead of looking that up in a database, we can send a get points RPC to this function and we'll just return the value of the points local variable. And then the only thing we do in this function, besides the handlers, is just await a promise that never resolves so that we're not returning from the function, so that we make sure it keeps running. And we can also like combine this with the cancel from the last one, like if we want to support like a GDPR, forget this user. So they have some way of returning or canceling this function from running.
Mark, that's a question.
Yep.
Basic. What's the difference between like an API call and doing a purpose?
I guess they're the same. Yeah. Any other thoughts on differences? They're both like requests over the network to either fetch data or do something.
So your forever function never stops, right? How you redeploy like new code?
Okay, that's a good question. How do I redeploy?
I have a different question. Kind of answer at the same time.
Okay.
Where is the state?
We'll get that to that one later. In what I've been describing so far, unless it gets unloaded, it lives in the memory of the process, at least there, but it's also in a database somewhere. We'll get to how that works. Your question, what if I want to change this code? Okay, good point. I want to add, so it depends on what code changes I'm making, and it requires the answer to his question, which we'll get to later. I guess some changes you can just deploy, and it works. Some changes you have to use one of two of the versioning APIs. One is like if version v1, then do the new code, or version v2, do the new code, otherwise do the old code. So that's one way. And the other way is deploy the new code alongside the old code, and any new functions that are started will be run on the new code. And any old functions that are continuing running will still run on the old code. And if you want the forever functions to move over to the new code, then you do something called continuous new, where basically you recurse and call yourself and give enough state that as an argument that the new invocation knows the status.
Was a previous volatile, right?
Yeah, so like if the loyalty program took a user and the number of points, then I called it with a user object and 0, that would be the first thing. And then notify purchase, I called that twice, and then points was 1,000. Then let's say I had a timer, so every day at midnight, I called continue as new. What that would do would be start a new loyalty program function, and I'd say continue as new user, comma, points, which has 1,000. So it's sort of like restarting the function once a day. And at that point, it could move over to the new code. That's a little bit complicated due to the way it works, which we'll get into a little bit. So to summarize durable execution, it's process independent. It has automatic retries of intermittent failures of dependencies. You can sleep for arbitrary periods of time. You can call RPCs on the function. Functions can work forever, and you can use local variables instead of storing things in databases. But how? So one common, where is my emoji? There's supposed to be emoji there. So one question I've gotten before is like when I described what it is, was like, okay, you guys must like not use RAM and using SSD for all the process OS memory so that you can recover. And that's not the way we do it. You don't need special hardware. You can run on commodity hardware. This is sort of the high-level system design. On the left is the application developers. On the right is the platform team. Or you can use our temporal cloud hosted service. All of these pieces, the client library, the worker library, and the server, they're all open source. You can host the server yourself. So the flow is, you start out anywhere in your backend application, you import our client library and you use it to start a durable function or send an RPC to an existing function. And that's communicating with the server. You like give it the address of wherever you deployed your server. And the server is a cluster of services and databases, including Cassandra or SQL, that has the event log. It takes care of the durability part, and it has an event log of everything that happens to this function. So it has like the start command and what the arguments were. It has any RPC command and what those arguments were, and like serialized and saved in the database. And it also has like everything that the durable function does. And any meaningful thing that it does during its execution is also saved in the event log. The server also has Elasticsearch so that you can search efficiently through your currently open or currently running functions or any past completed functions. It also has a web UI so you can see it all and like see the history of each of your functions, or if there's something running and there's a problem, it'll like show you not only what it's been doing, but also like where it's at right now and what the current error is and what the call stack is. So the last thing we have is the worker pool. So these are long-running processes that use our worker library. So you import it, you start the worker, and you give the worker your durable code, your durable functions. And what the worker is doing is periodically polling the server, saying, hey, can you get me a task? Any tasks for me? So in the situation of like the client starting a loyalty function, what did I call it? Loyalty program. So client would say, hey, start a loyalty program, here's the user object. Temporal server would save it, the first thing in the event log. They would then add that task to a queue of like, start the loyalty program function. A worker would pick that up off the queue. This is sort of like happening behind the scenes. You don't have to like know about this when you're coding. You're just explaining like how it gives the durable guarantee. So the worker picks up that command, that task, and it starts the loyalty program. In this case, it doesn't do much. So next thing that happens, so it's just waiting right here. Next thing that happens is the client sends an RPC. let's say notify purchase RPC for $100, and that goes to the server, gets added to the event log, a task gets added, the worker picks it up. When the worker picks it up, it already has this function in cache right here, waiting here, but it knows that it should now call this handler with that data, purchase data, and points changes. And we do that again, and let's say that the points total is 100,000 now. Whoops. Now let's say that the worker that had this function in cache and memory dies. Then we get a get points RPC from a client. So somewhere like the API server for the web UI of your product needs to display the points total. It sends the get points to the server adds it to a queue, a worker picks it up, the worker is like, oh crap, I don't have this function in my cache right now. Hey server, give me the event log of everything that's happened in the past in this function. Once the worker has that list, it knows, okay, there's a start loyalty program command with this user object, so I know I can call this, and I'm just gonna get stuck right here. And then I get like, oh, there's 2 notify purchase commands, RPCs, with these purchase objects. I will call those handlers twice with those different objects. Okay, now I can do I finished going through the past event log. I can now do my get points, and this points will be correct. So we can like guarantee that this new query is accurate and reflects all of the RPCs and activity that has happened in this function in the past. So that's how it sort of works in a nutshell. Here's sort of a family tree of some of the main durable execution systems I worked out here. Temporal, our co-founders, worked at Amazon and released sort of the first version of durable execution as AWS simple workflow framework. And that came out of Amazon being one of the first big companies to switch to microservices, and they soon realized, one, I can't synchronously call between microservices. It doesn't like work operationally. 2, okay, now we'll try communicating with events between all the services. That has a lot of issues and is hard to maintain and evolve. And then they landed on this simple workflow framework as a much easier way of coordinating between services. So one of the temporal co-founders went on to Azure to create durable task framework as like a new iteration, and it was so popular that it was adopted by Azure Durable Functions, which is a service they offer today. And they came together at Uber and built the Cadence open source project, which is used at Uber to orchestrate across 1,000 of their microservices. And they forked the Cadence open source project in 2019 to create Temporal and the company to improve the developer experience and reliability of code everywhere in the world. And so we have 180 people working on improving the product and spreading the word. It's used by a lot of companies, including Stripe, HashiCorp, Netflix, Snap, Coinbase, Datadog. It's like a durable function powers every Airbnb booking, every Snap story, every Coinbase transaction. So last section is system design patterns. These are some great resources, microservice.io lists patterns, and bytebytego.com is a great newsletter on system design. First one is circuit breakers. So if I've got multiple services in my backend, and they're synchronously calling each other, and I am service B, I'm getting called by service A, I need to do something that involves calling service C, and service C is like taking a long time to respond, or maybe it's returning errors and I'm taking a lot of time retrying. So I've got like these threads busy, like maybe waiting for a response. And I'm going to keep on getting requests from A, which means the number of threads I've got taken up will expand until I run out of a resource on my machine, like number of threads. And then I start not being able to respond to requests from A, which means that A will build up its number of threads and become resource exhausted, and that can be a cascading failure. So the solution that's commonly used for this is called a circuit breaker, where I'm B, instead of calling C directly, I'm going to call it through a proxy. The proxy will pay attention to how often requests are timing out, and once that hits a threshold, it will set a timeout and start immediately failing and not passing on any requests to C. So I'm B, I'm trying to reach C, I go through the proxy immediately returns unavailable. Once for the duration of the timeout period. Once the timeout is off, the proxy lets some requests through, and if they succeed, it'll let more through. And if they don't, then it will do another timeout and continue failing everything. So that's the circuit breaker pattern. It's not needed in temporal or durable execution in general, because it's sort of done automatically for you. It might look in your durable code like you're synchronously calling and waiting, but in actuality, it's being put on a queue and executed by another process and done async, and retries are done by the system. Event-driven architecture is a common way of communicating between microservices asynchronously. So there are a number of problems with synchronous calling, as we saw with the circuit breakers. So the solution is to, instead of like calling the service directly over the network, you instead publish an event to a event bus like Kafka, and other services are consuming those events, so subscribing to the events and publishing different events. So here's an example of what that looks like. The client on the left creates an order by posting to /orders. API server handles it, validates it, and then sends an order created to the message bus. The payment service consumes it, does the payment, publishes order paid. The fulfillment service responds to order paid, does the fulfillment, emits order fulfilled, and then any other services in the company can subscribe to any of those events. In this case, the analytics service is subscribing to all of them. So the probably main pro to event-driven architecture is people always say it's decoupled, and decoupling is great. The kind of decoupling that EDA has is at runtime. So if my fulfillment service goes down, or let's say my payment service goes down. Let's say my fulfillment service goes down. And in the synchronous land, my payment service would be trying to reach me and failing and get backed up and maybe lost fulfillments. But in this case, the message bus is a durable data store of the event log. And when the fulfillment service is down, the payment service can continue publishing order paid events, and that's okay. They won't get it fulfilled immediately, but whenever the fulfillment service comes back up, it can go through the backlog of order paid events. So they're decoupled in runtime in that when one of them goes down, the other one can still consume. The issue with this is that it is not that decoupled at design time. When you're building it, when you're designing it, when you're trying to evolve it over time. So let's say we are the API server team and we want to change the name, the type of the order created event. We want to call it new order. Or maybe we want to change the data that is in the event in a breaking way. We need to figure out across the company, across all the teams in the company, who is consuming this event. And maybe I can do like a search through their code, or maybe I have distributed tracing set up and I can like look through the past of what are all the other services what are all the services in the company that have responded to this event in the past. And I can just go with that list. Hopefully like there's no one that's currently working on and about to deploy a new service that depends on that event. But assuming I have a list, I need to go to all those teams and I say, can you please update your code to follow this new code format and let us know when you've finished writing it and deploying it and testing it so that we can update our code. And that can take a long time, that can slow down development a lot to be so tightly coupled during development. In durable functions, you have a much better developer experience and you can move more quickly because, first of all, the observability is better. I can see by either reading the durable function what steps happens, like what it calls. I can read, I can look, okay, create order, charge user, fulfill package, instead of like trying to, in here we had to like, I made it easy for you by like putting them next to each other and going down like that, but in actuality, it could be more complicated than that, and they're not going to be in that order, and you have to sort of, the order of which things happen is sort of like an emergent property of all of these teams working apart from each other, and it's hard to observe, grok, understand, and I want myself, my future self, and all my teammates to be able to understand quickly what's happening so that they can work in the system. So if I have functions that I can read the code of that shows the business processes, instead of trying to interpret the event sequence, I can understand this better. I can also like see what happened on the execution of all current and past functions by looking at their event history. So I can see, oh, some orders called the payment service, went through payment, and some just went straight to fulfillment because they had a credit or something. So, event-driven architecture, decoupled at runtime, not decoupled at design time. Durable functions, less coupled at design time, and better developer experience, but also decoupled at runtime. So whenever I like call something, like call an external service in my durable function, it's automatically getting put on a queue and retried in the case of failure. So the service I'm calling, I'm not dependent on them being up in order to run my code, because I have that automatic retrying built in, and eventually it will succeed, and then my code will continue. Sagas, aka long-running transactions, are transactions in which you avoid locking by having a list of separate operations that you do, and then if a particular operation fails, then you undo all the previous operations in what are called compensating actions or compensating transactions. And sagas are difficult to code correctly without durable functions, because you need to use some kind of like persistent event store. There are two ways. One is choreography, which is the event-driven architecture way. Another is orchestration. And Chris Richardson, the author of microservices.io and microservice patterns, basically generally recommends using orchestration because of the downsides of choreography being it can be really complex to understand, visualize, maintain, evolve over time. So he says use orchestration, but the downside of traditional orchestration is that you are defining the steps that happen, like ABC, undo B, undo A, in some kind of orchestration DSL or markup language like JSON or YAML. And that's not a very flexible or pleasant way to define logic. The best way to define logic is with code. You can read it more easily, you can be more expressive, and you can run it locally and you can debug it locally. So durable functions are sort of like a code-based way of doing orchestration. So you have the benefits of not being the complex choreography, and you don't have the downside of having to work in a markup language. So in a durable function, you can do a saga pretty easily. If we have this process order function with the 3 steps, inventory, service, reserve, and charge, listen, package, we can just use try catch. So let's say we reserve and then we charge, and then we try to send package, but it fails with some non-retriable error or application level error, like the address doesn't exist. It will catch the error here, and then we'll refund. So we're undoing the charge, and then we'll throw to here, and then we'll unreserve, undoing the reserve. So that's a saga, and I didn't need to do either choreography or I didn't need to feel like I was doing orchestration, although orchestration is just sort of automatically being done under the hood for me. Transactional outboxes. So when we're in event-driven architecture, a common thing we do is I'm a service, I'm consuming an event from the bus. I write to a database, like my own, I'm the payment service database, I need to write to my database. And then I also, right after that, I publish the order paid event to the bus. The issue with that is, so I'm the payment service over here. If I wrote this like payment record to my database and then I died before I got to order paid, then the fulfillment service won't know that it needs to fulfill the order that got paid for. So the answer is you need to get these two things to happen sort of in a transaction. And the way you do that is with a transactional outbox, aka transfer queue. So in the payment service, when I'm updating my data store, adding this like payment record, in whatever partition that data is located in, I need to also update in a transaction with that a local mini queue. And then I need to have, so I add the order paid event to this local queue. And then I need some other process to be pulling all the queues on all the partitions, the mini queues, provisionally taking them off, trying to publish them to the bus, if failing, retrying, if succeeding to publish to the bus, taking it off the queue. So you atomically get the event in the payment service database along with the payment service state update, and then you eventually get it to be published to the bus. So, and that's the way to in a fault tolerant way, do event-driven architecture, basically. And it's a pain to do because you have to do it every time that you publish an event. In temporal and durable execution, you don't have to use transactional outboxes because the entire problem was predicated on I do step A and I die before I do step 2. I write to my local database and then I write to the message bus. And the idea was that it's a problem if I die between. In durable execution, you can't die between. It's guaranteed that the rest of the steps of the function will execute. So you don't need transactional outboxes. Next up is event sourcing. Event sourcing is, next thing I have a thingy. Here's without event sourcing and then with event sourcing. Here, these aren't 3 separate rows in a table. They're a single row in 3 different states. So first you insert it and the quantity is 5, and then you update that row, order ID 1001, you set quantity to 6. And then you update it again and you set state to pay. The equivalent of this in event sourcing land is instead of having like a single row that you're updating and changing, instead you have an immutable event log that you're just appending to. So I insert this new order with quantity 5, and it's immutable, and so I'm not going to change this quantity right here. What I'm going to do is I'm going to append a new event called modify order that says I'm setting the quantity to 6, and then append a new event saying, okay, I paid for this order. And this has some benefits. It also has some drawbacks. One drawback that might be apparent is like, it's hard to query this to find out, okay, is this order, what's the quantity for this order and what's the current payment? I have to like read the history to figure it out. So instead what you do is you have some materialized read views that are getting the events as they're being written, and the read views are like materializing or aggregating these events similar to this into the current state of the model. And so all the writes are going to this table, and all the reads are going to the other databases or caches. So that's one issue. I guess the benefit is, a couple benefits are auditability. You can see everything that happened in the past. 2 is replayability. I can replay to any point in time and see what the state was. So in durable execution, event sourcing is sort of like done for you automatically, because we're already doing an append-only log of every event that happens. And yeah, that's just how we structure the database that we use. And it provides similar benefits to event sourcing, because it is event sourcing under the hood, and including the auditability. I can see everything that every one of my production functions did, and I can also replay them to a specific point in time, including like taking the history from a production function execution, downloading it to my local machine, and running it in a debugger, and setting a breakpoint on my code, and seeing what happened to that production function. CQRS is command query responsibility segregation. So commands are mutations or write commands, and queries are reads, and it's about separating the responsibility of them, sometimes just in the model layer, but I think usually in the database as well. So having a separate write database and read database. You can implement CQRS with event sourcing, but you can also do it without event sourcing. It sort of looks like this. Client talks to the UI. UI, if it's a write operation, talks to the command model, which talks to the write database, which eventually gets data into the read database, into a materialized view. Sometimes materialized, it could just be a copy. But usually it's like denormalized for the sake of read efficiency, query efficiency. And you might use a tool like Debezium for this, change data capture. In the event sourcing land, you might have used like Kafka is the message bus or event log sort, and you might use ktables as the materialized read views. And I guess in durable execution, you sort of like don't need to do this when you are saving state in a local variable instead of a database. That's part of it. Another thing is sort of the materialized view sort of is done for you in that, and is not eventually consistent, but is strongly consistent in that whenever you read or send a query RPC that returns data, like the get points, it's the function state is automatically getting materialized from all of the writes that have happened, and it always has an up-to-date view of all the writes. So it's consistent in that it has the accurate value of state that's getting returned. Distributed cron jobs. So if I want to do a cron,
So
I can.
before you move on to the next
Yeah, sure.
For CQRS, do you have an example of that? Because in my experience, there is always some time between the write and the read. So what kind of features or systems will you like that availability so that when you read, you know it's there?
I think, at least in this diagram, it's implied that you are not going to ever be assured that the read is accurately reflecting all of the writes that have happened. Yeah, because like it takes time for the changes to get propagated, and if you were always waiting for that to happen, you'd be like have high latency and then lower read throughput, I guess. Yeah.
Yeah, that latency is always seen in secure design, no matter what. If you're using any regular architecture, you see some latency. It depends on how you configure it, and you see the latency. It's not synchronous. You know, we write to the database, it doesn't come back to you.
But I think even in AWS where they are sure that we're gonna get the data within a second, there's still some time latency there. So that's what I'm saying. Like this is probably just used in systems where it's not as critical to read as fast as. Like we don't have to have exactly the consistency of the data. Like it's not as important.
Yeah, I imagine it's used where you don't need consistent reads, and it's okay for it to be eventually accurate. So I want to do a cron. I can set a cron on my Linux machine and deploy that out there. One issue is reliability. If that dies, then my crons aren't happening. Another is throughput or scalability. I might have too many crons for that machine to handle. In many use cases, you need some kind of distributed, reliable cron job solution, and it's really easy to do that with durable function because you can just do sleep, and you can have billions of these functions that sleep running in parallel, and you can also have really high throughput of like number of functions that are coming up from sleep or firing their crons at the same time. Task queues is a common general pattern of like, I have this work, I either don't have time to do it now, or I need to do it really reliably, so I need to store each step that happens in the work. One example would be like, I'm the YouTube API server, and I'm getting a file upload from a creator, and I need to like encode it in different formats and chunk it up and put each chunk in the blob store. I can't do that myself because I don't have time for that. I'm responding to the API request, and that's like what my resources are my like RAM or CPU is optimized for. I also like might not be around by the time this job is done, and I want it to be reliably done. I don't want to like my process to crash or get restarted and lose this video and whatever I was doing with it. So what I do is I write it to a queue, and there's a pool of workers that pick up parts of that task and execute parts of it, and like sort of report back in the queue whether they were successful. And there's some like intricacies like to that, like making sure that you don't take something off the queue until you're finished with it, and making sure that when you're polling, you're looking for not just new tasks, but also like tasks that have been provisionally taken but are like an hour old. So it must have been the fact that the worker that provisionally took it is no longer around and dropped the work. So I need to take that. And it's also a lot to code if you're doing all these writes to the queue and the polling yourself. And in durable execution, sort of everything that is done is behind the scenes being done with the task queue. We went into a little bit, but both when it starts, both when a function starts and when the RPC gets sent to it, those tasks are getting put on a queue. When the durable function calls sleep, and then it goes on a timer, and the timer goes off, that task is going on a queue. Even when the durable function calls a normal function that like talks to the network, like the send email or charge user, those are also going on a queue and being picked up by a worker. And that's sort of like all done for you. So that's really nice. Getting the benefits and the reliability and consistency of task queues without having to implement them yourself. State machines, particularly in conjunction with task queues, are a common pattern of I have this process that can go through all these states, and I want to chunk up the execution of getting between each state. And I guess like if I'm a worker, I'll pick up something in a certain state, do the work to progress to the next state, and then write it back to the queue. And I don't need to do all that work of like writing and reading and putting back in durable execution, because I can just store the current state in a local variable. I can still like structure my code as a state machine. I just don't have to do all the writing to a queue work. So that's all I got for design patterns. In summary, circuit breakers, I forget. Circuit breakers don't need, or sort of like are done for you automatically by temporal. Event-driven architecture, you're getting the runtime decoupling benefits for you with temporal, and you get better TX. Sagas, really easy to do in temporal, you just try catch. Transactional outboxes, you don't need to do. Event sourcing, done for you automatically. CQRS, sort of irrelevant, sort of done for you. Distributed cron jobs, easy to do. Task queues, done for you. State machines, easy to do. So we learned what durable execution was, talked about some new programming possibilities, talked about how it works, and some design patterns before and after temporal. That's some more information and Twitter handles, and that is the slides. And we have to answer questions. Oh, and we have stickers, if anyone wants stickers.
Right?
Oh.
Anticipating that there will be questions.
Jim thinks we have questions.
So,
Yes, sir.
so largely if you look at all these institutions, right, they're mostly on the design patterns that we talked about, right? But would you like to say that if we start using temporal, all the design patterns that we discussed are efficiently managed in any point in time?
Efficiently managed, yes. I believe so.
Wouldn't that be a big change for all these things to come out of the existing architectures to embrace temporal programming?
Yes, it is a big change, and a number of companies, including like Stripe, Datadog, HashiCorp, are working on that migration and are doing more and more use cases with durable execution.
The example might be somewhere like JP Morgan. We've spoken publicly about this, where anyone works for a large bank or comes from a large bank, very set in ways. The architecture might be archaic at times, and they're rebuilding payment systems using temporal. For this reason, it's a change in mindset to think about idempotency, not determinism. And then these patterns are a piece of that.
I work for Deutsche Bank and I also work in the payments arena. And I've been using all the design patterns that we just talked about. I was just trying to evaluate myself. That one is the best choice.
Yeah. Well, we should talk to corporate payments team based out of the UK. Deutsche Bank is currently implementing temporal. So we're happy to do it.
And the answer is yes.
Of course.
I guess so. To speak to Alex's point on determinism and idempotency are things that I talked about. So I guess one restriction we need to make on the code that's written is that the durable functions have to be deterministic. So they can't like do something like if random is less than 0.5, do this, otherwise do that. And they can't like talk to a database or the network because those are non-deterministic. Sometimes they might fail, sometimes they might, I don't know, have a bit flipped and have a different read. Or they might have a different result over time with like talking to a service that has different data. So you can't directly do those things inside a durable function. And the reason why that is, why we restrict the durable functions to be deterministic code is that we need to be able to replay everything that happened, all the events that happened in the past in order to get to the right state. And we can't do that if your code takes a different path, different times of So we separated, we called it workflows are the durable code, and activities are the normal code, like the send email function or the charge user function. And activities, since they're automatically retried, unless you set the maximum attempts, like change the default retry policy to set maximum attempts to 1, you need, and if you want them to be correct and retriable, then you need the activities to be idempotent. So pass an idempotency key to Stripe, and Stripe will take care of making sure that if it's called twice, it won't actually charge twice.
Okay, so if you have, you call it recursive reserialization of the state, that is, if you restart like the same process on different containers, how, like, the state that it's in, does each one of the microservices just contribute one piece of data to whatever current is, if that makes sense, or does it have to like go through the entire history of, you know, what transactions to the database to, I'm not even sure serialized, because it's hard to think of a data structure of a durable function.
Let me try.
Okay.
If
Sure.
you're not ready, I think I've got something. If I spit out nonsense, set me straight.
Sure, go ahead.
What I'm imagining here is that the temporal solution will work a lot like a CPU's scheduler in the operating system, where this so mentally move your model up a layer so that you're seeing instead of, you know, the way it works on the scheduler is you have to swap out one job and swap in another job to be able to multitask. And you've got the CPU that pretend you only have one core, can only do one thing at a time, but it looks like it's doing 7.
Sure.
And the way it does that is switch. And the way it does that is it takes the values of all the registers and writes them out somewhere else, and then it goes off and does another thing. And one of the registers says which line of code it was looking at, and another register says what state it was in, and all this other stuff. So what's going to happen with the temporal solution is it's going to take its state at that moment, save it, and that becomes the state that it resumes with wherever it happens to resume. Doesn't matter if it's the same core or different. Did that?
Okay, you're not.
Did that settle your puzzle?
Yeah.
Okay.
Just not.
Did I do okay, Lauren?
It seems so.
Is it good enough for you?
I was going to go down a different track, and
Yeah.
you can let me know if it's helpful. Is like,
I'll learn something.
if this handler is, instead of just multiplying by 100 for the total, if it calls some downstream service to say, okay, calculate how many points to give this user based on this purchase object, then, like, say we had 100 notified purchase RPCs, we'd have 100 downstream service calls, and all the results of all those calls would be part of this points. And then, like, after whenever we did our continuous new recursive thing, let's say a month later, we would call loyalty program user points, and like we don't need to carry with us the history of all of the service calls, because it's all the important state that we need to keep is just the total number of points. Yeah.
Okay.
And the reason why we need to do that continuous new thing is either for the versioning to get on a new version of code, or if the event history is too long. So we have a limit of 50,000 events per function execution, and the reason for that is that so that it doesn't take too long to replay from 0. So like, yeah. So when we do the continuous new and call the function again and restart it, we're starting from a clean state of 0 or 1 event. when is this code sent?
So if this code is executed, execution. So when are the events generated? Are there any points that can generate the events, or is it just this inside the code itself that it generates these events?
Where is the?
I think you're asking at what point does it commit? Like at what point does it become a plugin? Like at what point are you saying the state?
No, when are they sent to the different committed through the workers, they will do the commit. Isn't it after play that is? Yeah, this system.
Okay. The other one didn't do much, so that's a good example. So there's when execution history events are saved to the database in the server that was over here. Is the question. So one is when the client library is being used to start a function or send an RPC to a function. But I think the question is like, you can also get events added to the log based on what this function does. And there's three or four ways here that happens. Let's say we haven't gotten a cancel RPC, so we go to here, we're not canceled, await charge. So charge is talking to, let's say, Stripe. Talking over the network is non-deterministic, so this must be a normal function. So what happens is, instead of actually calling this code in this process, what happens is this is actually defined up here as like a proxy to the charge function. And the proxy is provided by the worker library, that open source that we publish. And what it does is it talks by RPC to the server and says, hey server, schedule this charge function to be called with this user and this amount, and add that to the log. Similarly, when so the worker will, a worker that has the charge function and the charge task queue, it will query the server, it'll get that charge event or task, it'll call charge until it works. Let's say it fails, it'll send the failure to the server, that'll be added to the log. The next retry will be scheduled based on the retry policy, like 1 second, 2 second, 4 second. Once that timer goes off in the database, the server will add another call charge task to the queue. The worker will pick it up, it'll execute again, talk to Stripe, succeed, return the success value to the server, which will write it to the log, and write an event with the result that gets picked up by the worker that has this function. This promise resolves to that return value. In this case, we're not using it, but we could have some value returned there that we saved and did something with. And then we go to the next line, and then sleep is also imported from the worker worker library basically. And under the covers is talking gRPC to the server and setting a timer in the database. So these are two situations in which commands or event logs, execution logs are being generated by the durable function.
I have a question. So you mentioned that we should try and avoid using non-determinism within durable execution. On that note, I was just wondering if durable execution maintains the train completeness of the programming language it's using.
Yep. You can do anything in the programming language. It's not like a limited DSL.
Okay.
Depending on the language runtime, you are either have to educate yourself and prevent yourself from doing it, or you have a static analyzer that'll tell you you did this wrong, or like in Sandbox or in Node, we use V8 isolates to run your function in the isolate with a redefined like math.random, so that and redefined date, so that if you're using them, you get a deterministic version of them.
Is it available in Java?
Yes. So we've got these runtimes or libraries that you import. TypeScript/JavaScript is for Node, PHP.NET, Python, Java. We have some Kotlin helpers, Go, and then the open source server is implemented in Go.
It's all right.
Pardon?
That's all right.
And we have let's see, a community contributed Haskell SDK. Apple might be working on a backend Swift one. I think someone maybe is working in Clojure, I forget. But
There's Clojure one, Scala, Ruby.
Okay, right.
Got no Fortran? Awesome. Thank you, Lauren.
Thank you.
Okay. Thanks for having me.